Welcome back to our class on machine translation. Today we're going to talk about decoding. This is the process of actually producing a translation for an input that comes along. In machine learning, this is also called inference, but we'll keep with the machine translation jargon here and call it decoding. We're going to explain decoding specifically for phrase-based models, but actually the decoding algorithm for neural models is pretty equivalent and has the same kind of challenges that we deal with here. So this is pretty universal. So let's take a closer look at what problem we have to solve. So in the last lecture, we came up with a nice mathematical model that for every foreign input sentence and given foreign English sentence E, you get a probability. So we had a nice formula that kind of breaks down, given the phrase segmentation, these and these numbers get added up, language model scores also on, fancy reordering model and so on. If you have a given foreign sentence and a given English sentence and a phrase segmentation, you got a number out relatively easily. So, but the problem we have here is to find a translation E best that has the highest probability. So we basically want to solve this problem. And so you can naively say, well, let's just look at all the English sentences in the world, except there are probably infinite many English sentences of the world, especially if you don't put a limit on length of sentences. But even if you put a limit on the length of the sentence, there's exponentially many. So we can't just list them all up. So this is the problem we want to deal with today. So another thing is worth pointing out is there are two types of error that can happen when you go through this process and produce a bad translation. So one of the errors is that the most probable translation that is being produced, this E-best that actually satisfies this equation, is just a bad translation. And that means something is wrong with your model, so you should need to fix the model. Another one is that yes, your model would actually give the translation that it gives the highest probability to, that translation might actually be a really good translation, but search doesn't find that most probable translation, and then you fix the search. So the best way to actually evaluate decoding is by look at search error, not at the quality of translations. Although these are often correlated, a decoding algorithm that just doesn't find the best translations according to the model often is then also not producing very good output. But if you compare different decoding algorithms, really the metric should be the probability of the best translation that it found. And a decoding algorithm that finds the highest probability translations is a better decoding algorithm, regardless of the translation quality. The translation quality at that point is a problem of the model, so we need to fix the model. So we have a very narrow problem we try to solve here. We trust the model at this point, and we try to find the best translation according to this model. Okay, so let's go through maybe a human translation process first to get a sense of how this decoding algorithm might be set up. So it's a really hard task. You have to produce a whole sequence of English words. So this might be a German sentence, a very short sentence. Er geht ja nicht nach Hause. And we want to translate that from German into English. And as someone who might know this, I'll just give you the literal meaning of the word. So this means he goes, that word doesn't really mean anything, not to house. So I said this word doesn't really mean anything. It actually has this nice linguistic term of a flavoring particle. It gives the sentence a bit of a jolt. It's really hard to say what it really means. Maybe similar words in English are like words like just. This is just not that interesting. That's not interesting. This just doesn't really add all that much, but it kind of gives it a bit of a jolt. So this is this kind of word. Yeah, for the content words that actually matter, he goes not to house, so this should become he does not go home. So how does a human translator would go about this? Well, they would say, let's first start with the subject. You have to translate the subject, which is er, becomes he. So you pick a phrase um, in the input and translate it. And then you say, what's the next word? And in English, you would now say, well, we have to, since it's a negated noun verb phrase, we have to get the negation first. So this ja nicht becomes does not. So that's the next thing you would pick. So something really interesting to observe here is what happens here is actually reordering. We produced the English word sentence in sequence, but we didn't process the German word sentence in sequence. So we jumped around on the German sentence, and that created a reordering operation. So this is how reordering happens in a translation process. It just basically means reordering means not picking source words out of sequence, but jumping around in that. So what's the next thing? Well, we're gonna go and produce a verb. He does not go. And translate that into go here. And then we just basically finish up the phrase with nach Hause. It just becomes home. He does not go to home. It doesn't sound so good. So he does not go home. It sounds much better. And that's the translation. So what are the lessons we learned from this? So we don't have to worry too much about reordering, structuring that as a kind of data structure or setup problem. Reordering means taking words of the foreign words out of sequence. It's still a problem. And translation we're gonna do by building the sentence left to right. So one thing that you might already realize that really benefits any kind of scoring with a language model, because we produce the words in sequence, so the language model gets kind of one word at a time and can score it. So this was our probabilistic model, the kind of the basic standard model for translation, and it consisted of phrase translation probabilities. So that means in our case, at inference time, each time we pick a phrase to be translated and pick a translation for the phrase, we basically have to look up in a big table what score comes along with that. This year you have to track how reordering happened, what was the end word of the last foreign phrase that we translated. So we need to keep that in mind at each time. So we only care about what happened in the last phrase, what was the last word, which position was it. And then there's a language model. So the language model, we have to keep in mind what was the previous English words we produced. Since the language model is an n-gram language model with a limited history, we only have to keep track of a certain number of English words. So not all English words matter to score additional words, only the last, let's say 2, 3, or 4 different words, depending on the order of the language model. Okay, so now we're gonna try to replicate the process that we just did as human translators as an algorithm for a machine. So the human, we just kind of made arbitrary decisions that came out of nowhere that just sounded right and felt right, and that's why we did them. A machine doesn't have the benefit of having that kind of intuition. So this is what the machine has to deal with. So it has a lot of different translation options, and this is a real phrase translation table, again, trained on European Parliament proceedings text. And it's just really a small subset of what's possible here. So for each phrase like he, we kind of pick the top translations. And also for phrases, so two-word phrase, so here are the top translations, here are the longest phrases that we have translations for. Geht ja nicht. In the actual reality, if you actually train a phrase translation table, as we discussed last lecture on the European Parliament proceedings, you get for this particular sentence 2,727 matching phrase pairs. For each phrase translation probability, especially for common words, there's a huge tail of junk. So it doesn't make sense to say, well, okay, let's just ignore all that junk at the end. We can only look at the top 20 translations per phrase. That's probably good enough. And then in this case, still 202 translation options remain. Keep in mind, this is a very short sentence. Average newspaper sentence is maybe 20, 30 words. This one is 6 words. And you have 200 translation options to deal with. These are the ones you should have picked. So these are the ones that the machine has to pick. And not only does the machine has to pick these, it also has to pick them in the right order. And making this, picking them in the right order makes this, it's kind of a naive setup, an exponential problem. There's an exponential number of orders how you can go through the sentence. So what we're gonna do, since we are not gonna solve an NP-complete problem here, is to come up with a heuristic algorithm. So what I'm having here in the picture is a display of the phrase translation table, just like as lines, just to give you some sense of that. There are all these options how to translate the foreign sentence. So we're going to start this process with a data structure we call hypothesis. So this is the initial hypothesis. This is how we start with. So this data structure contains a couple of information. One is here on top, we have basically a bit array that checks off have we translated words. So all these are now white boxes, meaning nothing has been translated yet. And in the middle, we're going to put in information like what was the last phrase that was generated. So here at the beginning, nothing happened. Okay, it becomes more clear if we actually translate a word. So we can expand this hypothesis into a hypothesis that actually has some kind of content in it, where we decided that we take the second word and translate it as R. So there's here this translation option where get gets mapped to R. So we pick any translation options. So you see on the top all these lines there. We can pick any of them. Any of them that we pick, we create a new hypothesis. So we have all these possibilities. As I said, there are 202 different translation options. So there are actually 202 different hypotheses that we can generate here. Then we're going to continue from there on and basically produce additional hypotheses. So here's the one where we started the sentence with he, one of the 202 possible translation options. And then there's various ways to expand it. Again, we can pick almost any of the phrase translations. We can translate the word he again, so that eliminates some of them, but there are probably still over 100 choices at this point. And these are the choices we have here. And so on and so on. And let's say we're going to expand this one as well. We're going to expand pretty much everything. And ultimately, we're going to end up here. And that is the best translation for the sentence, hopefully, that we find, if this has the highest probability or the best score. So if he does not go home has the best score, then that is the translation we're going to return. Okay, so this, you already see the big problem with this algorithm is that it completely blows up. So what can we do about it? So one thing we can do about it is dynamic programming. So the suggested translation process creates an exponential number of hypotheses. There even has been a mathematical proof that machine translation decoding is NP complete, which as computer scientists you know means it's impossible to do anything reasonable for big N, and N being here the number of words in the sentence. So basically we should abandon all hope for sentences longer than even 5 words. So in order to deal with that, we're going to do two things. One is recombination. So this is the dynamic programming, which is actually risk-free. So that means we're not going to run the risk of missing the best translation, the translation that the model assigns the highest probability to. And since that is not enough, we're also going to do pruning, which is risky. There we might actually lose the best translation. So here's the basic idea behind a recombination. Especially with the way we conceptualize the phrase-based model, it is possible to produce the same output in multiple ways. So we could translate first the word it from the first German word, and then we produce the word is from the second German word. So you have now the first 2 words covered, and we produced it is. But we could also have just a phrase translation of the first 2 words into it is. Both are possible ways, and at this point, well, these are really identical. So there's no point in pursuing both of these paths going forward. One of them has a better score up to now. By a better score up to now, I mean all the phrase translation probabilities factors in, all the language model scores factored in up to this point. And well, there isn't much in terms of reordering, but any kind of reordering scores or any other score that matters up to this point factored in. So since we now really have an identical hypothesis in terms of coverage and output, and one of them has a higher score than the other, we can throw away the one that has the worst score. And we might keep a back pointer here. We'll actually do this only if we're really interested in the search letters, and sometimes we're interested in the search letters. It actually is more powerful than that, because there might be situations where we can actually also recombine hypotheses that are not identical. Let's look at this example here, where we said one translation started with the word he, and then we produced the word does not, the words does not. So in this case, we have the first, third, and fourth word translated. And here we start with the word it, and then produce the word does not. And again, the first, third, and fourth word are translated. So under some circumstances, we can now drop the worst of these two hypotheses as well safely. And that has to do with what future scores might still happen here when I continue. And if I continue from here and make the same operations here, and I get exactly the same scores as when I do the exact same operations here, then whatever is better at this point should be kept and is better, and the other one can be ignored. Here are the conditions of when this is true. So if I have the same foreign word translated, so whatever comes further, you can do exactly the same for the worst of these two hypotheses. If the same 2 English words in the output, the same 2 English words are at the end of the output, does not. This is assuming a trigram language model. So the language model still looks at the last English words that were produced. So the score that I'm adding here is still impacted by the last 2 English words. But here in this case, the last 2 English words are the same. Again, this is assuming a trigram language model with a 4-gram, 5-gram model, but that's not as the same anymore. And also, if the last foreign word, that has to do with reordering. So we ended up with translating this word here last, and that's the same again in both cases. So that's also the case. So under these circumstances, because all the feature scores that I attach to this path are going to be identical when I make exactly the same decisions on this path. And if the one is better than the other, then the other will never be able to outcompete the first one. So the worst hypothesis can be dropped here as well, and maybe we keep a back pointer or not. So here are the restrictions on recombination. And that impacts a lot about the feature functions you might want to add. And there's some feature functions that just put too many limits on recombination, so that might actually be a problem. So the translation model. So the nice thing about the translation model is that the phrase translation and operations are independent of each other, so there's not really any restriction on hypothesis recombination, unless you count which foreign words have been translated. Obviously, that's a restriction. The language model looks at the last n-1 words for n-gram language model. So for recombination, those have to match. And for the reordering model, like a distance-based reordering model based on distance to the end of the previous input phrase, they have to match as well. So the recombined hypothesis must have the same end position. So other feature functions might introduce additional restrictions. Last time we talked, for instance, of the operation sequence model, it might have also additional restrictions because the previous operations might be different. Okay, so that's pretty powerful, but it's not gonna buy us, get us out of the NP completeness of the problem that we're dealing with. So we have to do something else, which is called pruning. So recombination reduces search space, but not enough. We still have an NP complete problem on our hands. So pruning is the idea of just removing bad hypotheses early. If I just make completely arbitrary crazy choices at the beginning, and maybe I put like two words next to each other the language model hates, one is the 5th word, the other one is the 17th word, that's just not going to look very good. So maybe I can recognize that early not to have these kind of crazy choices. So the way we do this is we put comparable hypotheses into stacks. So hypotheses that have translated the same number of input words, for instance, that's how we're going to organize it here. And then we limit the number of hypotheses in a stack. So we're going to compare all these hypotheses in a stack and throw the bad ones. It's actually much easier to explain this with a picture. So we have all these stacks here, which mathematically, from a computer science point of view, they're not really stacks, they're just really sets. So this is the first stack, which has no word translated, so that's not really a stack. This is a stack that has all the hypotheses that have one word translation. It doesn't matter which one, so it might be the first word or the second word. So when we start translation, and actually this is an example how translation happens. So translation happens by taking one of these hypotheses and expanding it in all possible ways. So expanding in all possible ways creates new hypotheses that can be put in the stacks that are to the right of it. They have more words translated, so it's always going to be to the right of it. So the decoding algorithm is really moving through the stacks and then moving through the hypothesis in the stacks and producing new hypotheses. So these stacks fill up, and if they get too full, we cut them down. So we might say a good number is maybe 100 hypotheses or maybe 200 hypotheses per stack. When it gets bigger than that, we look at the one that has the worst score and just throw it away. That gives it a very simple decoding algorithm. So we place the empty hypothesis in stack 0, and then we move through the stacks. Then we move through the hypotheses in each of these stacks. Then we look at the list of all possible translation options. And if it's applicable, meaning it doesn't conflict with coverage, so it doesn't translate things that we already translated, then we create a new hypothesis, paste it in the appropriate stack, and also check if it can be recombined. And if the stack gets too big, we're going to throw away the worst hypothesis out of the stack. And that's it. So we have here a nested structure of 3 for loops um, which yeah, tell us something about the complexity of the algorithm. So this is the length of the sentence. So this is our n, so it's at least ON. Hypothesis stack, this is going to be some constant. And translation options has something to do with how many possible translations there are for input words and phrases. So it has something to do with the length of the sentence. But one thing we're also going to do is we're going to limit reordering to a window. So this actually essentially also becomes a constant. So this algorithm is linear. Okay, here's the whole thing spelled out with a bit more math. So the different pruning strategies. One is histogram pruning. So what I just alluded to, we only keep k hypotheses in each stack. Another way is to say we're not going to keep hypotheses that are factor alpha worse than the best score. So the computational complexity is maximum stack size. That is a fixed number. Translations options, that has something to do with the length of the sentence. And then the sentence length, this is really how many stacks there are. So it is quadratic complexity unless you put in also a reordering limit. And if you put in a reordering limit, so typically this is done distance of 5 to 8 words. If you actually don't put in this reordering limit, you typically get worse translations. The one thing that kind of encourages the reordering is the language model. That looks at good word sequences, and if it's given free reign of picking words anywhere out of the sentence, it just puts together words that don't really fit together at all in the meaning of a sentence, but just the language model likes it, so it doesn't really do very well. So it also kind of in general, you get better translation quality. It depends a bit on language models, the hyperparameter you could tune. But this makes then the number of translation options a constant because it always goes over the same size of window of input words. So that makes the whole thing a linear time algorithm. Okay, let's take a closer look at how we eliminated translations from a stack, how we actually did that pruning. So here's the motivating example. So let's say we have this foreign sentence here, the tourism initiative, English sentence actually. The tourism initiative addresses this for the first time. So what I want to highlight here is it has like this trigram, the tourism initiative, and the trigram the first time. And you could start the sentence with translating the tourism initiative, and this is what we do up here. So we translate the tourism initiative, or you could start the sentence with translating the first time. The tourism initiative has a bunch of unusual words in it, like tourism and initiative, which maybe the translation model likes these possible translations. So here it translates, for instance, tourism in touristische, which becomes an adjective. So that's, since tourism is a noun, it's not the most likely way, but that's the one that fits here better. So maybe the translation model doesn't like it too much. But the key difference probably will be the language model. The tourism initiative is just not a very usual English phrase, so the German translation of it, it's also not going to be a very usual German phrase. So the language model is going to just say, okay, these are some odd words. They're not necessarily wrong, but they're odd words. So it gives it a bad score. These are log probabilities here. While the first time, that's just a pretty standard phrase that's been used many, many times, and that's something that the language model is going to like better. So key difference being here, the language model doesn't like that first phrase so much. It does like the second phrase much better. Yes, in terms of reordering, the first one it doesn't do any reordering, so it's happy with it. And the second one there is some reordering involved, so there's some cost implied, but still overall, the cost for the second one is better than the cost for the first one. So why does that all that matters? So both hypotheses translate 3 words, and the worst hypothesis starts with the end of the sentence, has a better score. So if it becomes a pruning to choose between the two, it would throw away uh, the translation that starts at the beginning of a sentence. To put it kind of in very simple terms, if we prune by the cost of a hypothesis, then we encourage it to translate the simple part of the sentence first. So translating the easy part of the sentence first. So maybe you should have a more refined estimate of future cost. So if you're comparing apples and oranges, if you compare hypotheses that translate different sentences, then maybe we should be a bit more careful about the cost of the apple and the orange. I think this metaphor kind of lost its track. So, future cost estimate. So how expensive will it be to translate the rest of the sentence? So if I translate the easy part first, then I have to account that the rest of the sentence is going to be more expensive. So I should factor that in. So this is how we're going to do. We're going to be optimistic. We're going to say, what is the easiest way to translate the foreign words? And we know for each possible phrase translation the cost. That's actually previously known. Language model is not so clear. So we know the output words, so we can score them. Are these unusual output words? So that gives you some estimate, but we don't know the context. There might be these really unusual output words, but there might be some context where they just fit in beautifully. That's we can't do because that's only going to reveal if we really put words together. So that's a more expensive estimation. Reordering model, yeah, we don't know how much reordering is going to be. We can ignore that. Maybe we know from the current hypothesis, if it has words out of sequence, we could factor that in somehow. Here is the cost estimates from translation options. So what we did here is we looked at a word like the, looked at all its possible translations, and not only the phrase translation probability, but also the language model probability. So here, if it's a single word, just the unigram probability, and then pick the best one. And these are now log probabilities for all these possible choices. So this would, for instance, tell us that that's pretty cheap, tourism is more expensive, initiative is expensive, addresses is expensive, initiative addresses is expensive too. Things like this, the first time as a whole phrase is actually pretty cheap, and so on. So this comes out of the phrase translation table. So for each translation option, we can compute the future cost estimate, and then when we go over a sentence, we can just look up all these future cost estimates for any word or phrase. So this gives us only coverage over spans for which we have phrase translations. So we have to expand that into spans that go over, like any span that go over anywhere in the sentence. The way you read this chart here is we start at different words here, and then we go a number of words further. So if this is for this here is for the tourism, this is for the tourism initiative, this is for the tourism initiative addresses. And here we start with the word tourism. So all the phrases that start, all the spans that start with tourism, just the word tourism, tourism initiative, tourism ministers addresses, and so on. And we basically can pre-compute this. So at decoding time, what we're gonna do is we not only compute the cost of the hypothesis so far, these are all the costs that are accumulated, but we also look up in that previous table how expensive will it be to translate the rest of the sentence. And in this case, this might be minus 6.1 as a log probability. So we add up these two numbers, and then that's the actual cost for this hypothesis. While this translation here, where we started with the easy part, so the cost so far is lower, but we still have to translate this part here, and it's quite expensive, 9.3. So when we add up these two numbers, it's actually worse. Or here's another example where this for time was translated as for this time. It just kind of really randomly picks up words out of the sentence that kind of the language model likes. So the language model is pretty happy about this sequence of words. So the cost so far is not that bad, despite a fairly high distortion cost. But we still have to translate this span, which costs 6.9, and we still have to translate this span, which costs 2.2. So putting everything together, it becomes also pretty bad. So what we're comparing now at this point is the combination of cost so far and feature cost. Tourism initiative for the first time, this for time. Okay, this is basically it in terms of the core ideas behind decoding. We're gonna now look at two variants of decoding that were more recently proposed and became then standard in the models and are conceptually a bit more complicated, but are more efficient solutions. So this is how our pseudocode for the stack decoding algorithm looked like. So what we had here is these two loops here. So we have to go over the stacks. We're not going to change much about that. And then we had two loops where we look at all the hypotheses in the stack and all the translation options that are applicable. We're probably going to combine these two things. So we're not actually going to loop over all the translation options, but we're already going to limit ourselves by the window of where we can pick translation options from, and then just look over those translation options. So this loop design probably is a bit smarter than looping over all the translation options. So in practice, what this means, we actually loop over all the possible spans where we can pull translation options from, and then loop over those translation options. Anyway, so this is still what we do. We loop over all hypotheses and all applicable translation options. So we can group these hypotheses by a coverage vector. So we're going to organize this a little bit more tightly now. So we're going to group the hypotheses all the hypotheses were generated so far by a coverage vector. So these are all here hypotheses that have 3 words translated, but some of them have the first 3 words translated, some of them have these words translated, and so on. So why are we grouping them? Because each of these groups can be matched with the same translation options that follow. But here I can apply different translation options than there. So here, this is the first one, I can't translate this word again, but in the second one, I still can translate this word. So then I also group the translation options by span. So these are all the translation options that translate the 4th word. Here are all the translation options that translate the 5th word, and so on. So that's what I'm trying to indicate here. So this is what I'm doing first. I'm looking at the hypothesis in my stack and group them by coverage vector, and then I look at all the possible translation options and organize them by the span. So then for each of these setups where I have a particular coverage for words that translated so far and a particular span that I might pull translation options next, this becomes a square, or a rectangle actually, to be precise. So in this case, let's say there are 6 different hypotheses and there are 5 different translation options. In reality, these numbers tend to be much bigger than that. So given these 6 hypotheses and 5 translation options, we now basically try all of them out, and we basically try out 6.5 6 times 5, 30 different options. So this is quadratic, roughly. Do we really need to explore all of them? So this now has nothing to do with like how big the stacks are going to get. That's another story. It's just, should we even do the computation to produce unlikely things? And the idea behind cube pruning is to not do that. So first, what we're going to do is we're going to rank these hypotheses by score. So this is our most likely hypothesis so far, the second one, and so on and so on. They all have the same coverage, so the future cost actually is for all of them the same, but otherwise I could factor in the future cost here. These are the possible translation options, and they have all different scores. So this is a score that might also include the language model, expected language model cost. So you might actually take the future cost here to rank this for the translation options, not the actual probabilities. So score estimate, not just the phrase translation probability. So if you would fully expand this, maybe this is how it looks like. All these numbers are clearly made up. But yeah, we combine the first two, and this gives us a score. If you just kind of add up these numbers, this is what we get. So this is our estimated score we're going to get. The real score will be different from that because we will actually compute the real language model cost of attaching the word go to this phrase, and not just the unigram cost for go, which went into the estimate. So if I look at this table and saying, well, let's just explore half of them, well, this pretty clearly informs which half I should explore. Probably this part here. And this is what we could just do here. What I'm going to talk about here right now is going to be even more sophisticated. So we only compute half. We just say, let's just compute this half. So cube pruning is doing it a little bit differently by iteratively computing these translation options. So we actually have this matrix here in the back of our mind that we just did by simply summing up these costs. But now we're actually expanding this hypothesis. We're actually going to build this. And we might find out that, yeah, the estimate was 4.2. We're actually going to end up with 3.9. Because the word go actually fits in really nicely. He does not go, that's a pretty nice phrase. So the language model might actually like this better than we would have expected the word go going kind of anywhere. Okay, so we actually expanded this hypothesis with a true cost. We actually can deal with this, but we also had the computational cost of producing this. Now we explore the neighbors of that. So the one to the right, the one to the bottom. The one to the right looks slightly better. So we create this neighbor. We have to actually expand these hypotheses and build them, and all the scoring that involves. Next, we're gonna expand the one. We're gonna basically say, okay, this is a good one. This is the best one of the two. So we commit to it. So we actually add it to the stack. And then we explore its neighbors. So these are now the new neighbors. At this point, you would say, sorry. At this point, we would say that this one looks best next. So this is the one we're going to commit to next and explore its neighbors. And we kind of do this for a specific number of hypotheses. You also have to keep in mind that this is one particular group of hypothesis and translation options. So there are various groups, and they all basically are arranged in a way that they compete with each other. So we look at all the possible groupings. Each of them has, we produce the top right corner hypothesis for each of them, and then we kind of choose between them based on which one looks most promising, which has the most promising scores, and then expand its neighbors and go from there. I'm just going to quickly say this algorithm was originally proposed for syntax-based decoding models where you had another dimension, which was the non-terminal symbol. And you also had the way the rules were set up, a more complex setup for the phrases involved there. That's why it's called cube pruning. A better way to look at it here is really, this is not a cube, it's really a rectangular display of options we have to go through. Okay, let me finish up with one more sophistication on top of this idea, which I'm calling here Hayfield pruning because it was proposed by Hayfield in a paper on more efficient decoding algorithms. So the main idea here is, or maybe I should say that before, what is really costly about hypothesis generation, it looks like not really a very costly operation. It's just phrase translation probability, that's a number you pull out of a table. The reordering cost, that's a really simplistic calculation. Language model also seems to be just a table lookup. However, the language model is a table lookup over a gigantic data structure. So if you pull out numbers from a gigantic data structure that is all over the place in RAM, you're going to get a lot of cache misses and so on. So it's actually very expensive. So this is something that becomes really expensive. The most expensive thing in decoding is the language model lookup, because just by its nature of having to query a data structure that is often gigabytes big. So we want to avoid that as much as possible. So back to this idea here. So the main idea is that a lot of the hypotheses share suffixes. And a lot of the translation options also share prefixes. So the kind of scoring you have to do there at the boundary is often very similar. So combining the last word of a hypothesis with the first word of a translation options might already indicate if we should pursue this any further. So just seeing in our example, for instance, he does go and does he went, no matter what context that is just bad. You can also already tell from this bigram of the last word of the hypothesis and the first word of the translation option if this is something worth pursuing further. So the method here now is to organize the hypothesis by a suffix tree and organize the translation options by a prefix tree, and then process a priority queue based on pairs of nodes in these trees. Okay, we're just going to go over an example to explain that. So let's say these are hypotheses that have two words translated. So we're still kind of at the very beginning of this whole process, and we translated things either into a big country, a large countries, the big countries, a large country, the big country, a big nation. There seems to be some ambiguity about if it's singular or plural, which is not all that uncommon. Maybe we translate it from Chinese, where that is not even indicated in the Chinese. And then we continue with some kind of verb phrase, but we don't know if it's does not waver, do not waver, wavers not, does not hesitate, does rarely waver. So there's all these options here too, which is not uncommon for maybe the next one or two word verb phrase. It's a negation and a verb. So we organize this in suffix and prefix trees. So this is for the translation hypotheses that we have so far. So there are a bunch of ones that end in countries. There's a couple of ones, a few ones that end in country, and there's one that ends in nation. And the ones that end in countries are the big and the large. So this is, if you look up here, the large countries and the big countries. So this is all there. What we the numbers we put in here are the minimal cost we have to pay, the minimum cost you have to pay no matter what. So if you kind of walk through this, there's one way to get only 2.2, and that is large countries. That's 2.2. The big countries is a bit more expensive. It's 2.7. So if we add these things up, then we get there. That's the structure of the prefix T. So the arcs are with the most optimistic cost, and then basically expanding from there. We're doing the same with the translation options. So there are a couple ones that start with does, actually quite a few of them, but then only one that starts with do and only one that starts with waivers not. But there's a bunch of them that start with does. Okay, so these are just the data structures. How do we use them? So as I said, we have a priority queue that tells us how to expand the space here. So again, naively, we just combine all the hypotheses with all the translation options, but that gets too expensive, so you don't want to do that. So we do it a little bit more cheaply. So the priority queue says we have these two nodes here. And for that, we can also compute the minimal score, which is here 2.1 and 1.1. So that's the most optimistic based on future cost estimates for translation options and actual cost for hypothesis of how this can be combined. So that's our queue. So this is the thing that we pop things off from. And there only is one item in there, so we pop that off. And then we can either expand the hypothesis or we can expand the translation options. So we're first gonna expand the hypothesis just arbitrarily. So we're gonna go through this and find the cheapest way we can expand it, and that is this 2.1 here. So we're gonna add country, and this is the translation option is still unexpanded. So this is basically this 2.1 we pulled out of there. So the score didn't actually change. And that gets added to the priority queue. And then as an alternative to priority queue is, this means we still started the route, but we're skipping the first best option from there. So we have to expand it further. That means this is not anymore available. So what becomes available at this point is this 2.2, and that's what's in here now. So it's our priority queue at this point is now these two things. We just added both of them, and we're gonna pop off the better of the two. And so this gets us here, and now we're expanding to the translation options. So what is the best choice for the translation option? The best choice for the translation option is does. So that's what we're gonna do. Okay, so now we actually have two actual words. We have the word country and we have the word does. So we have those two words, and we can actually now compute the bigram score for that. Do they match up? Is that a good pairing? And does country, yeah, that's a pretty good pairing. Country does, yeah, that makes sense. So previously, what we factored in was a probability of does in isolation. So it was just a unigram probability. Now we say does following country, and that's a good spot for the word does. So we actually might update our language model probability based on the actual computation we did there. So we actually had to carry out a computation now. This expensive language model calculation that we don't want to avoid. And we add this plus 0.2, so it actually becomes better. So this is the new item on the priority queue that happened because of the expansion. And then we keep note of, yeah, there are also other ways. And the other ways are now not anymore this way, but only those two. And the better one is this one, 1.5, plus the 2.1, which is this 2.1 here. Okay, we're gonna keep doing this now. We're popping off the next item, which is country does, which is it seems to be on track towards kind of the right path. Next word is big, so we're expanding to the left here. So country, big. That also allows us to update language model scores, and this is still a good match. So big country does still a good match. Big country we already knew is probably a good thing because actually we got it from the data, but big country does definitely helps. So now we have 2.9, and then we say what are the alternatives from there, and so on and so on. And we basically keep doing this process. So the priority queue kind of expands further and further, uh, where we have probably one path we kind of pursue until we hit a roadblock, and then as alternatives become more popular. And here all the alternatives form that one path that also expanded in various ways. So once we have a full combination complete, we add it to the stack. We then actually have a hypothesis that actually is a fully formed hypothesis we can add to the stack. Um, so, so whenever we come across things like countries does, which it's really not, the language model is really not gonna like, this is gonna get pushed down here in this priority queue. So it's gonna get ignored there. So this is the benefit of this variant of the algorithm, that if it encounters kind of bigrams or trigrams that the language model really hates, that it doesn't even expand the full hypothesis uh, and translation option combination, so it doesn't actually just have to score the whole thing with the language model. Here's some charts on performance. So the Moses algorithm is the pruning algorithm that we talked about earlier, and this work is this refinement, the Hayfield pruning, that is more efficient. It's worth pointing out that there are two ways this is evaluated. I started out the lecture with this argument. This is looking at the average model score, so which scores are actually given to the best translations. And you can see here, if you spend 1 second on a sentence, you get much better model scores for this refinement of the algorithm. Another way to evaluate it is in the actual translation quality, and that is a bit more jagged curve. It's arguably also not the right way to evaluate a decoding algorithm. It is somewhat interesting to keep that in mind, because that ultimately what matters at the end. Yes, you do all these improvement in decoding algorithms. Does it matter? And so here it says, yes, you actually get better translations. Okay, let me wrap this up with kind of briefly surveying other decoding algorithms that were proposed. So one is A-star search. So if you look at, if you come from artificial intelligence, A-star search was the one big heuristic that was used all over the place. So why don't we just use it here? Greedy hill climbing was a very early a way to do decoding, which also takes a very interesting take on how to do decoding, which is worth knowing. And the other one is why don't we just use existing finite states transducers? And there was a whole research group that kept doing this forever, and in the process also improved finite state transducer toolkits. So A-star search, for those not familiar with this, is basically the kind of heuristic search we did so far, but it also has two properties that are slightly different. So it also has a future cost estimate, which had to be admissible. So this is the key difference. So admissible means, this is a technical term associated with A-star search. It means it cannot overestimate the cost. So in our case, this would be in terms of the one cost that we're estimating is the language model cost. So what is the best possible language model cost for this word? Is there any context where this word fits in beautifully? And that's the cost we're going with. So that would be an admissible heuristic. So what does that enable you? So if you do basically decoding and try to first kind of complete one path, you get one possible translation, and it has a certain score. So that means for any other translations I produce, even if I'm not completely done, but if I combine the cost for the hypothesis with its future cost estimate, which is now optimistic, and it's worse than a completed hypothesis, I can stop searching there. So I can throw these ones out. So this does imply that I kind of have to first complete some hypothesis all the way to the end before I explore the entire search space. So the decoding is probably less incremental right to left, but a bit more depth first. But otherwise, it's quite similar. In practice, we don't really do that because if you do this, it just in practice doesn't reduce the search space sufficiently. The search space is still gigantic, and if you actually then do this, you would explore too many hypotheses. So it's just not a strong enough restriction on search to have this limitation on a hypothesis to be expanded based on admissible future cost heuristics. Another idea is greedy hill climbing. So this is a quite different take. So this idea is let's just create one complete hypothesis first with depth first search. So just basically what's the best translation options here? Okay, let's take it. Let's take the next one. Let's take the next one. Just complete the sentence. We first translate a sentence in the best way we can based on just basically stack decoding with a stack size of 1. Then the idea is we have now a complete translation and we can improve it. So we basically take this hypothesis and see if we can find better hypotheses by just fixing it up a little bit. So what if I change a word translation with a different word translation, or phrase translation with a different phrase translation, or combine translation of 2 words into a phrase, or basically all these different ways how I can manipulate this translation with just one step and see if it gets better. So you have to define a number of operations, how to change this translation by either swapping out words, maybe reordering 2 phrases, and seeing does it improve things. And the idea is that this is a limited number of operations, so then I can choose from all the possible operations I can take, the one that actually helps, and if I can't find an operation that helps anymore, I'm done. This clearly has a problem that I might get stuck in local minima, but then I also can do a look ahead and consider 1 or 2 possible expansions. So there was a very early implementation of this for the IBM models, which decoding is really messy and complicated, which was popular for a while, but it really has been succeeded by the beam search that we talked about here. One nice property of this algorithm, though, is that you can just time limit it too. Since it creates an initial hypothesis initial translation really fast, you can just say, let's go with that if you're in a hurry, or you can say, okay, you have half a second to improve it, and then I'll take what you have there. So you can actually guarantee that you get translations within half a second, no matter what. Okay, so here's a summary. So the way we first looked at translation is that we translate sentences left to right, and that informed our decoding algorithm. So the way the decoding algorithm is set up is that we have to choose among translation options of translating source phrases. And then decoding happens by a data structure we call hypothesis that we expand by basically taking hypothesis, combining with the translation option, having new hypothesis. And then they had 2 basic methods to reduce the search space. One was recombination. If they're either identical hypotheses in terms of output words they've produced and source words they covered, we can throw one of them away. And the other one was a bit fancier, which also looks at what actually impacts future scoring. So we can actually throw away even more. And the other one was pruning, which requires to do well also a good future cost estimate. And then we looked at other decoding algorithms, cube pruning, refinement of cube pruning called Hayfield pruning, and even A-star search and greedy search and so on. And that's it for decoding. So some of these concepts will become come back to us when we talk about decoding in the context of neural models. But this is a kind of a fairly nice introduction to the topic. And that's it for today.